Hi, and welcome back to C Beginner to Pro series. In this video, we'll be dealing with Boolean Algebra. Now, before we delve into Boolean Algebra, I just want to motivate why I believe it needs to be studied. With the help of Boolean Algebra, you'll not only be able to write more complex if-else statements, but you can also analyze your program in a more theoretical fashion to see if there's an issue, what could be causing it, by analyzing how does your if-else propagate throughout things. It will help you reason about conditionals in a more structured manner. Now, what is Boolean algebra? It is similar to the mathematical algebra that you might be familiar from school, where you have numbers and you do different operations on them. You do 5 plus 3 equals 8, and then you have 5 plus 3 equals x, and so on and so forth. It is similar, however, your units would not be numbers, so as in mathematical algebra, but instead you'll be dealing with Boolean values. So everything is either true or false. All of your variables, all of your things evaluate to Booleans which are true or false. Similarly, in mathematics, everything evaluates to a number, right? And everything is a number. Yeah, as you can see, expressions that evaluate to true or false. You can see an example of a Boolean algebra statement in the fourth point, which you can read as A and not B, or not A and B. This will become clear in a second. And most of your Boolean algebra, you'll be dealing with truth tables, unlike in mathematics where you might use calculators or, just by, or just doing the math in your head. In Boolean algebra, mostly you do on truth tables. So what is a truth table? Well, here's a truth table. You can see on the bottom I've written the expression A and B, or in brackets not C and B. So what is a truth table? You can see A, B, and C written on the top of the columns, right? A, B, and C. And then truth, true, 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 false, 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 true, true, false, false, true, true, false, false, and so on. So you can see these are all the combinations that your variables can take. So A can be true, B can be true, C can be true. And then at the last column, you write for this row assignment, what does the expression here evaluate to? So for the assignment true, 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 the expression as a whole evaluates to true. And we can verify this in a second once we understand the different operators of Boolean algebra, right? So there's a little bit of science, or sorry, not science, but a method, how you fill out the truth table so as to make sure that you have fully covered every single combination of assignments for A, B, and C without duplicates. As you can see here, first I write 4 truths and 4 falses for A, and then 2 truths, 2 falses, 2 truths, 2 falses for B, and then for C I alternate. So the more practice you will have with truth tables, the more you'll understand how to fill them out properly. For now, I don't think it matters that much. What you need to know is that truth tables grow exponentially. So if you are familiar with combinatorics or permutations, if you have 3 variables and each of them can hold 2 values, those being true and false, there are 2 to the power of 3 possible assignments, right? So the first one can be true or false, the second one can be true or false, and the third one likewise. And when you do all the combinations 2 times 2 times 2, this gives you 8 possible assignments. And as you can see, our table has 8 rows. And this has exhausted all of the combinations for A, B, and C. Now, moving on. So we saw what a truth table is. It lists all of your true-false combinations. We know that if we have n variables, we have 2 to the power of n rows, and we have n plus 1 columns, right? Because we need the last column for our expression. What does the expression evaluate to? And yeah, this is written there as well. So let's dive into the operators. The first one, the exclamation sign, you put it in front of a variable. It says we negate the value that's right after the exclamation sign. So it's a logical not, if you're familiar with them. So what happens? True. If you have not true, it becomes false. If you have not false, it becomes true, right? It's negation. It results into the opposite. So you can see this here at the bottom. If we have A in our truth table assignment, we have true and false for it. And then for the expression not A, we have false and truth. So true becomes false, false becomes truth, right? And this is our truth table for our not operator, and it exhausts how the not operator behaves. It's a unary operator, so it affects only one Boolean variable. or Boolean value rather. Because if you put it in brackets as in the previous one, so you could have put the not in front of the whole parentheses, this would negate the result of the A and B. But this will become clear in a second. So our next operator, which is the AND operator, written with 2 ampersands, it is true if both A and B are true, right? So what you're saying is A and percent B, as you hear in the expression. This only results in true if both A and B are true. False in all other cases. So A and B need to be true for E to be true. E stands for expression. And you can see the truth table again here in the bottom of all the possible assignments that we have, right? So true, true, false, false, resulting in truth only when we have A and B equal to true, and false in all other cases. And the last operator, the 2 lines like this next to each other, is the OR operator. It is true if either A or B are true, or both of them are true. It is only false if both A and B are false, right? And you can see here at the bottom where if A and B are false, A or B becomes false. This is not quite like how we use in language OR. We say this or this. We kind of mean exclusive OR, so not both things at once. But in logic, when we say OR, we mean an inclusive OR. And this is important to remember. And with these 3 operators, you can do all of the Boolean algebra expressions. You can reduce the more complicated ones to any of these combinations. You can reduce any more complicated Boolean expression to use only 3 of these operators. Technically, you need only 2 because with not and one of the other, you can express the third one. But this is slightly more complicated. Right. So these are our Boolean operators. We see not or negation, the 2 lines next to each other, which is an OR, and the 2 ampersands, which is an AND. Now, some languages may have a single line or a single ampersand for OR and AND, as well as the other ones. And there's a slight difference between them. C does not have this. I want to point out that in C, you don't have these operators down here that we see. We only have the top ones on 3 up there. Usually, there's a slight difference in these 2. In C, we have short-circuited operators, and I'll explain what this is in a second. However, on the bottom usually is how in some languages you write eager operators. The reason for this is, if you take over here, for example, let's take our OR operator. If we have A equal to true, right? A is equal to true. The expression evaluates to true in all cases that A is true. So if we see that A is true, we don't need to evaluate what B is. We can save some computational power by not evaluating B, and we can, make things easier for us. So if A is true, we just immediately say, oh, the whole expression is true. We don't need to evaluate what is on the right side. This is short-circuited ones. Similar for AND. If A is false, in all cases, the expression would also result in false. We don't need to evaluate what happens with B, right? If A is false, A and B would be already false. So you can save yourself some time. This is not the case with eager operators, which will, no matter what happens on A, will also evaluate B. And there are some, sometimes there will be some slight differences in how a program will behave if you replace a short-circuited operator with an eager operator. However, these are very contrived, and I'll show you some now, but in theory, you will never write such a program in your life. I will provide the Wikipedia article in the description, where you can find more information about these short-circuited and eager operators. Anyways, just to demonstrate my point, we have our online GTB here. Let's hide this away because it's giving me annoying ads. And let's construct a global variable a, which in the beginning will be equal to 0. Right? This is accessible by any function in our program. And then remember, we don't have booleans in C, we have ints. Booleans are the same as ints. So let's create f1, which all it will do is it will increment a with 1, and then we'll return is 5 less than 6. 5 is not less than 6, so this will in some way or another evaluate to false. And then let's create a second function, which what it will do, it will also increment a by 1, and it will return is 7 greater than 5, which should return something that is equivalent to true in C. And now let's do this. Well, let's keep the print because we'll use it for something. Let's do if f1, let's call f1 and f2. So if f1 and f2 are true, we want to print hello world. And let's at the end print the value of A. Yeah, I just made a small mistake. I meant here to write 5 greater than 6, which is not true, right? 5 is indeed less than 6. At the time of writing this, I did say that 5 is less than 6 is incorrect. So let's replace this with 5 greater than 6 and run our program. And we'll see only 1 being printed, right? So the value of A at the end of the program is 1. Okay, let's assume we don't know what the short circuiting thing is, and we only understand what if and statements are, and what is it. So what happens is we go inside here, we go through here, we increment A by 1, and we return 5 greater than 6, which is false, so this evaluates to false. And then what is the other value? F2, we run F2, we increment A by 1, so A becomes now 2. We return 7 greater than 5, which is indeed true. We have false and truth, which evaluates to false, so the if statement is inside the true block is not evaluated. If we had an else statement, it would be printed. So if we print here, hello world, let's print something else, let's just print 2, 2, 2, 2, right? We'll see the 3 2s instead, because this evaluated as a whole to false. Now, our A does not become 2, because as I said, it is a short-circuited operator, it's not an eager operator, so F2 is not called. So that's why only F1 is called, and A is incremented only once. If F1 evaluates to true, as it did in the beginning, 5 less than 6, we'll see hello world and then 2. Because then we have executed F1, which incremented by 1, and then F2, which incremented by 2. If we change this to false, we'll see again 2 and 2, 2, 2. So we're in the else block, however, A is 2 this time. This is because we had to run F1, which was true. We can't short circuit here yet. We need to see what is the value of F2. Is it true? Is it false? We can't make any statements about the whole expression until we find out F2. If F1 is true, in the case that we have an AND operator here, what is F2? Well, it increments A by 1 and it returns false. Similarly, if we had OR here, right, and let's make this, now this is true, this is false, right? So we should see hello world, because F1 or F2, F1 is already true. So we should see hello world 1, right? However, if F1 is false, again, let's make it false, we'll see 2, 2, 2, 2, because F1 and F2 are both false. And so we ran through both F1 and F2, and we got 2 for A at the end. If F2 is true now, so we have false or truth, the whole expression evaluates to true, so we should see hello world 2, right? And that's what we expected to see. So just to get back to the slides, if we have a short-circuited operator and we have OR short-circuited, if on the left one, so the first one evaluates to true, we don't need to evaluate the second one. For the AND short-circuited operator, which is the AND, if on the left side we have a false, we don't need to evaluate the thing on the right. We can immediately say this will evaluate to false as a whole. This is important to know to reason about some of your programs, but as I said, you'll never write a program like this example. And it can help you understand why in some other languages you have logical AND and a logical OR in 2 different manners, right? So to practice a bit more, I have written here a few expressions. Okay, so let's take our trusty Paint and write out the program in here, sorry, the expression in here, which was A and not B, A and not B. These are not the proper ways you should write in Boolean algebra. They use different notations for AND, NOT, and whatever, but I'm sticking to the computer science ones, the one we use in C, just because the thing is going to make things easier for you to understand. And then we have OR, not A and B. Alright, so this is the expression we need to evaluate. We have, I apologize for my poor penmanship, it's a bit hard to write with a mouse. Let's make our truth table. We have only 2 variables, therefore we need only 3 columns, right? A, B, and the expression. However, I will make 2 extra columns so that we have this and this evaluated and then 2 of them ORed. So this will be E1, this is E1, and this is E2. There we go, E2, and then the big E. And since we have 2 variables, we have 4 assignments, which are, so the way you write it is you do half of your total assignments for your first one as true and then half of them for false. And then you, for each next one, you alternate by a half. So since we have 2 here, right, 2 truths, for this one it becomes 1 truth, 1 false, and then 1 truth, 1 false. When we do more variables, it will become more clear how to do it as a whole. Right, so if A and B are true, the first expression, we have truth and not truth, which becomes truth and false, right? Which as a whole, because it's an AND, evaluates to false. So we have truth and false. Remember, AND is only true if both if both the first and the second operator are truth, which in this case one of them is false. So this E1 expression evaluates to false. And then we have not A and B. So we have false and truth, again evaluates to false. And we have false or false, which evaluates to false, which is the only case in which an OR operator gives you false, when the thing on its left and the thing of its right are false. As I said, not is a unary operator, but OR and AND are binary operators. If you don't know what that is, it's beyond the scope of this video, so I won't go into details. Now for the next assignment, truth and false, we have truth and not false becomes truth, so we have truth and truth. We have E1 evaluates to truth. Now we can short circuit it here and say, oh, we don't need to check what's on the right, we already have a truth. But for the sake of the exercise, let's see what happens on the right. We have not truth, which becomes false, and false, false and false evaluates to false. We could have short circuited again here since we had a false here, but we're just doing this for the sake of the example. We have truth or false evaluates to truth. So the whole expression in this assignment evaluates to truth. Then we have false and false. E1 evaluates to false. And then we have truth and truth, because we have not false. So not false becomes truth. Truth and truth becomes truth as a whole. So we have false or true evaluates to true. And then for the final assignment, both of them to be false. We have false, we can short circuit, right? False and not false becomes truth. You know, false and true, still false. Same for E2. True and false, because not false becomes true. True and false becomes false. And we have false or false, which still gives us false. So this is what the expression as a whole evaluates to for each of the assignments. So if A and B are true and false, or A and B are false and truth, we have the expression evaluating to true. It's false in all other cases. So that's how you usually go through truth tables or Boolean expressions. It does take a bit of more time. At some point it becomes more intuitive, but it is exponential work. It is NP hard problem, if that means something to you. Doesn't matter what it is for now, but yeah, it can be a bit annoying to make these whole things. Now let's look at our second expression, which in our case is A and not B or C. Now the reason I wrote this expression here, A and not B or C. Just how in arithmetics you have like an order of operators, right? You know your PEMDAS, products, whatever, multiplication. I'm not sure what PEMDAS stands for. We don't do PEMDAS. I just intuitively know in what order to do my arithmetic operations. Similarly, in Boolean algebra, you have an order of operations. So first you do negation, then you do OR, and finally you do your ANDs. With, of course, parentheses taking priority as a whole. So you have this similar thing to PEMDAS, but a PNOA. It doesn't sound as nice as PEMDAS, but usually just get in the habit of writing your parentheses just so you know what happens. So if we put our parentheses, this now can be a bit ambiguous how to read, but if we put our parentheses in the manner that we want things to be read, so first we do our nots, then we'll do our ors, and finally we'll do our and. So this is the order of operations. First this not here, then this expression here, and finally this whole expression here. Right, now we have three variables, a, b, and c. So we have 3 columns. I'll make again E1, which is this thing, the or here is E1, and then just E as a whole. And then 3 variables, so 8 assignments, 2 to the power of 3 gives you 8. So you have half of them are truths here for A, and then the other half you write falses, so 4 truths, 4 falses, right? And then for half of the half you do B, so 2 truths, then half of the half falses, and then true, true, false, false. And then for C you do half of the half of the half, so true, false, right? This should become pretty clear how to do it. The more you do these kind of things, it will just become a second nature to you, right? So expression 1 in this assignment, in the first assignment, we have not B becomes false because not true becomes false. We have false or truth, E1 evaluates to truth, and we have truth and truth evaluates to true. And then we have for the second assignment not true, so false or false evaluates to false, and then true and false evaluates to false. Next assignment, true, false, truth. So not false becomes true. True or true gives you true. And then true and true gives you true. Then we have true, false, false. So not false becomes true here. We have true or false becomes true. And then we have true and true becomes true. And here we can, short circuit, because if we have false and whatever, it's always going to give you false here for the whole expression. So as long as A is false, this expression would never become true. So it only in 3 cases is this expression true. In the case that B and C are both true, in the case that B is false and C is true, and in the case that B is false and C is false. Right, and we don't need to evaluate this thing here. So I would recommend going through the other expressions by yourself and trying to understand what happens, why these things happen. As you see, you can now write more complicated Boolean expressions, more complicated conditional expressions, which will allow you to write better code, more sophisticated code. And I will end this video, again, for the sake of simplicity here, and I'll leave the example programs for the next video, or just straight up leave them for the tutorial. As you can see here, I have written a few example programs you can try for the tutorial. I won't do them now, and I will go there a bit more in depth into how you can write more complicated if-else statements. Anyways, thank you for watching this video. If you found it helpful, consider leaving a like and subscribing. It greatly benefits my channel, and I'll see you in the next video.